Example 6.1. Lenses are ground from flat glass discs with either a radius of curvature of 40 or 60 centimeters. What is the focal length of each lens, and is it converging or diverging? To determine the focal lengths of lenses, we use the lens maker equation. And that is here is that I say that 1 over f, 1 over the focal length, is the index, and that 1 here is for air. So it goes from air into glass. And then I have 2 radius of curvatures right here, where R1 and R2 are the first and second refraction surface. So a key thing to using this is the sign convention. The sign convention is different than what makes things real or virtual. So the sign convention goes something like this, is that if the radius of curvature lands on the right side, then this quantity is a positive R value. So anything where its radius of curvature lands on the right side, that is positive. On the other hand, the left side is negative, then its radius of curvature for R has to look like that. Okay. Now, what you want to do here is that if you look at lens 3, it turns out that it could either be 40 centimeters or 60 centimeters. But if you look at lens 3, the curvature of the first one is closer to is shorter, and therefore that means here, I'm sorry, the outside of lens 3 is shorter than the one of the inside. So I'm going to assume that lens 1 is always 40 degrees. So let's go look at that. So I'm going to look at each of these lenses in turn. So here I go. So this is lens 1. And what do I know about lens 1? Well, let's paste it in. So if I paste it in, this is lens 1 right here. So when I look at lens 1, I can clearly see that this is a symmetric lens where R1 and R2, the magnitudes, are equal, and I'm saying that this is 40 centimeters. So we have to look at lens 3 to determine which radii is 40 centimeters or 60 centimeters. And I'm saying that this is 40. So now here we go. So what I'm going to do here is I'm actually going to bring this down here because I want this to be the middle of this guy is going to be where my central axis is going to go. So this is my central axis right here. So all incident light comes from the left. So this is our incident light. And it's coming from the left to the right. And then our center of the lens is this guy right here. Now let's look at the first surface. The first surface is what does the incident light interact with? So the first surface has a ray, interacts with this curve, and this guy, look at this. This has a curvature. So that means somewhere over here is going to be its radius, R1. So you could see here is that this guy is the first surface. So if that's the first surface, you could see that R1 is on the right side. So this guy is positive because its radius of curvature lands on the right side. Now, in a very analogous way here, so now the second refraction surface is this guy that light interacts with. And you could see here is that this guy is the second surface. And when you look at its radius of curvature, it's going to land somewhere over here. And this guy's going to be R2. But because it's on the left side, that's negative. So that has a negative value right there. So let's start to look at what's actually happening now. So what you're seeing here is that what do we physically expect? Since the lens is thicker in the middle, than the ends, it has to be converging. So if we do not get a converging answer, a converging lens answer, then there's a mistake someplace. So then, so if I look at my sign convention, then that means that R1 is now positive 40 centimeters. R2 is now negative 40 centimeters. That's what our sign convention. Now the lens maker equation says this. So this should be F1 is then going to be n minus 1 times the quantity 1 over R1 minus 1 over R2. So let's put in our numbers. So then our number says that this is 1.5 minus 1, so that's 1/2. So now look what happens. I have my first term, but this is positive 40 centimeters. And then I have my second term, and my second term says that this has negative 40 centimeters. So when I compute this, I then see here is that F1 is then equal to positive 40 centimeters, which is, of course, positive. Because this is positive, we then say that this is a converging lens and forms real images. So in other words here, if I was to just do a very quick ray diagram of the situation, it really says this here, that if I have a ray that comes in like this, that these rays are going to get refracted effectively if it's thin enough, and they're going to cross on the other side right here. This right here is the focal length. And that focal length from here to here is then 40 centimeters on the right side. Okay, let's go to lens 2 now. Lens 2. So when I look at lens 2, it looks like this. So what you're seeing here is that you could see that one side, the left side, the first side, is flat, which has an infinite radius. Okay, so if I now do my central line here, what do I see here? So you could see here, again, this is my direction of my incident light. So if I look at this thing, here's what you're seeing. This is the first surface, right here. And here it is right here. This is my first surface. My second surface looks like this. So you could see that right here, I'm going to have a surface R2, but that's on the negative side. So that means this guy has to be negative. And again, this is my second surface. And then over here, we see that R1 has to be infinite. So let's start interpreting what this lens is saying here. So the first thing that I would say here is that note that the lens is thicker in the middle. And if it's thicker in the middle, that must mean that it's a converging lens. So if I look at my radii, this guy here is going to be infinite, whereas R2 is going to be minus 40 centimeters. So let's look at the lens maker equation. So just putting in the numbers immediately, here's what we get. So the first thing that I get is I get that this is 1 over infinity, and then I get minus, and then the second one here is going to be minus 40 over 1. And so if I compute this, you're seeing here is that F2 is then going to be positive 80 centimeters, which is positive. That's a good sign, because if I have a positive focal length, that means this is a converging lens, and we knew that already, and forms real images. So if I look at this guy, if I just draw a little ray diagram, a very, very quick little ray diagram, look what actually happens. I have light that comes in parallel to the central axis, and that means here that if I pick this to be the middle, the refraction occurs, if it's thin enough, I can't tell the difference. And that means here is that this location here is going to be F2, where this distance is now 80 centimeters. Now, one of the things that we can ask here, what happens if we reverse the lens? Is it still converging? What I'm really asking is that I'm asking this question. Suppose I come back in here and I paste this guy now. Okay. So I'm pasting this guy right here. And so I'm asking, what focal length am I going to calculate? Well, if this is my central axis, what am I seeing here? Again, here's my incident light. It's coming from the left to the right. And you could see that now my surfaces look like this. This is my first surface, right? This is the first surface. And then my second surface is this guy right here. And we could see that this guy right here, this is the second surface. And when I look at this guy, what am I actually seeing here? What I'm seeing here is that I could have a focal point, R1, that's going to be, of course, positive. But if I look at my second surface, it doesn't really matter what side I put it on. It's going to be R2 equal to infinity. So is it still converging? It better be. Why? The lens is thicker in the middle. So if it's thicker in the middle, it has to be converging. And now we reverse the role of R1 and R2. So now R1 is positive 40 centimeters. R2 is infinity. So now if I look at the lens maker equation, look what I get. I get 1.5 minus 1. Now I reverse the roles of these guys. So this becomes 40 centimeters. And then I get minus 1 over infinity, which in this case then tells us that F2 gives me the exact same focal length. So I have the exact same focal length. So in other words, reversing the lens does not change the focal length. Okay, so now let's go to lens 3. So now we are on lens 3. So what do I know about lens 3? So here is lens 3. So let's draw our central axis. And again, as we've been stating again and again, this is the direction of the incident light. Well, the one thing that you could see here is that there are two possible radii, right? Either it's 40 centimeters or it's 60 centimeters. So then the question is, which side is 40/60 centimeters? And what you got to do here is that you have to draw out the curvature. And what do I mean by that? Look at the first surface. If you look at the first surface, look at the curvature. Right? So this guy right here is the first surface. Now look at the second curvature. So if I follow the second curvature, you could see that the second curvature here has a larger radii. So what this tells me here is that R1 in this case has to be positive 40 centimeters. And then R2 has to be positive 60 centimeters. It has to have a farther out one. So again, let's follow the same process. Again, the lens is thicker in the middle. If it's thicker in the middle, it has to be converging. We've already identified the radii. We said R1 is plus 40 and R2 is plus 60 centimeters. So now if I look at the focal length, again, just going directly to the numbers, I have this guy here. I have 1 over 40, then I get minus, and I get 1 over 60. Note that that square bracket automatically gives you a positive value. So then this immediately tells you that F3 in this case is then positive 240 centimeters, which is again positive as expected because it's thicker in the middle. So this again is a converging lens and forms real images. So if I look at this thing, I can play the same type of game as we did before. So if I paste this guy in here, and if I make this smaller, just to draw little tiny ones, and if I come over here and I reverse the lens, like this here, what you're going to see here is that if I draw rays coming in, it doesn't matter whether they come in looking like this or if they come like that, they're both going to give you a convergence on the right side. And so this focal length right here is F3, right? That's the focal point, but the focal length will always be the same here from the center to here. In this case, this is 240 centimeters. Now, just, let's say, suppose one picked the radii incorrectly. What do you get mathematically? Mathematically. Well, that means what I'm really saying here is that suppose you picked R1 to be 60 centimeters and R2 to be 40 centimeters. Now note that this is not the same as before. We reversed it. Now look what happens. If I punch these guys in, I'm then going to get 1.5 minus 1. And then what I'm going to get here is that I'm going to get 60 centimeters minus 40 centimeters. Note that this is a negative number. So then this implies here is that f of 3 is then minus 240 centimeters, but that can't be right. Why can't it be right? Because it's thicker in the middle. So you better have a positive focal length. This is negative. So this immediately tells you that this contradicts that thicker in the middle is converging. It's not a diverging lens. I'm going to do lenses 4, 5, and 6 simultaneously. So this is lens 4, 5, and 6. So if I punch these guys in, here's what I'm going to do. I'm going to paste them like this. And what I'm going to do here is that you're going to see here is that I'm going to start drawing in the central axis. Okay. Ooh, I don't like that. Let me try that one more time. There we go. Well, now, what you're seeing here is that if you look at each of these lenses, so each of these lenses are thinner in the middle, right? They're thinner in the middle than the edges, so that implies that they're diverging. And if they're diverging, that means here they do not form real images. They only form virtual images. So let's go look at the radii of each of these guys here. So here we go. So the first thing that I would look at is that let's go look at the surface. So this is the first surface. So if this is the first surface, then, okay, this is the first surface. So that means, in this case, that means that R1 is minus 40 centimeters. And if you look at the second surface, this tells me that R2 is positive 40 centimeters. And if I continue to, so again, this is the second surface. And if I look at this guy, look what happens. This is the first surface. And you could see here is that R1 in this case is infinite because it's flat. But if I look at the second surface here, this tells you that R1 is positive. Oh, nope, that's R2. Positive 40 centimeters. And then finally, if I look at this other surface here, what I'm seeing here is that I have to pay attention. So if I look at this guy, look at the curvature, right? Look at that curvature. Now let's look at the next one here. This curvature goes like this. So you could see that there's a distinction, right? Here's the second surface. You could see that R1 is smaller, R2 is smaller than R1. So then that means here is that this guy tells me that R1 must be positive 40 centimeters. Again, this is our second surface. And R2 is going to be positive 60 centimeters. So now if I start to do the focal lengths of these guys, I'm going to see this here. So I'm going to have 1 over f4. It's then going to be 1.5 minus 1. And then here we go. So R1 is negative. So this guy's going to be minus 40 over 1. And then I'm going to get minus, and then I'm going to get a positive 40. And look at that. You could see that I'm going to get a negative value already. So then this guy tells me that F4 is then going to be minus 40 centimeters, which is negative. So this tells me that the focal length is on the same side as the incident light. Now let's go calculate lens 5. So if I look at lens 5, this will be 1.5 minus 1. And then this guy's going to be something like this. So then I have 1 over infinity. And then this guy is going to be 40 over 1. And you could see here is that this guy tells me that F5 is then going to be equal to minus 80 centimeters, which again is a negative focal length. And then if I look at 6 here, 1 over f6, again, this is 1.5 minus 1. And then if I put in my values, you could see here is that in this situation, I'm going to have 60 over 1 minus 40 into 1. And that gives me a value of f6, which will then give me minus 240 centimeters, which again is less than 0. So therefore, it's a diverging lens because it has a negative value. Now, if I was to punch these guys in and just draw a ray diagram for these guys, here's what you would expect to see here. So I have light coming in, and because the light is coming in, it gets diverted away. So then what I do is I follow where the rays cross back. And this point is what they call f of 4. And again, this lens would tell me that it comes here to the middle of the lens. And then what does it do? It refracts away. And then I follow the rays back. And where the rays appear to be coming from, that's our negative focal length. Again, if I look at this guy, and then in this case, this is a longer one. So if I was to draw these carefully, we would have to follow these back, they don't get spread out as much, but it looks like that.